Now, it is with great pleasure that I introduce Dr. Richard Giles, who will be presenting on the topic of leisure marine radar. Richard obtained his BSc in physics with electronics from the University of Liverpool in 1975 and his PhD in computer science from the University of Manchester in 1979. Towards the end of 2020, Richard retired from Raymarine after more than 20 years working within the leisure marine industry, designing radars and their displays. Prior to this, Richard spent several years working in the computer graphics industry. Richard is listed as an inventor of more than 10 patents on radar and sonar, and I have personally had the pleasure of working with him on and off for over 15 years. I therefore ask that you kindly welcome Dr. Richard Giles.
Good evening, everybody, and thank you for attending this presentation. I joined Raymarine as a contractor for a few weeks. I retired having worked for them for more than 20 years. Initially, I worked on radar displays before, which became multifunctional, displaying more than just radar, and in particular on sunlight readable displays, which other companies with common interests such as aircraft and banking and bank ATMs used as well. And what was interesting about that is it was involved looking at the physics as well as the engineering. My radar work has encompassed both Magnetron and the relatively recent move to solid state radars. Radar engineering is fascinating and covers everything from motors to microwaves. I'll be talking about the principles and the products from the main leisure marine radar suppliers. So today I will look at leisure marine radars and discuss the various types of radar, their construction, typical installations, what's displayed to the user, and how it helps them, and touching briefly on future developments. There are two types of radar antenna used: domes and open arrays, and the transmitters of magnetrons, and more recently solid state. And solid state transmitters are either FMCW, continuous wave, frequency modulated continuous wave, or pulse compression. And solid state radars have been only recently been used because of the relatively high cost, and up till now have been really exclusive to the military domain. So radars are smaller and lighter, and they're more suitable for sailing craft as there's less likelihood of tangling with ropes and sails. And the open arrays are often more powerful. They require more current to turn the array in the wind, but they have better angular resolution in proportion to the length of the array. So a 4 foot in the ratio of the length. So a 4 foot to 18 inch is 2.6. So an 18-inch dome has a typical typical beam width of about 5 degrees, and a 4 foot open array 1.8 degrees, and a 6 foot down to about 1.2 degrees. We'll see later on why that makes a difference. So these are typical dome and array installations. So we have here a sailboat with the dome on the back, and a rib used for, in this case, London lifeboat, and then down here an open array on a fishing boat. And the dome here in both cases needs to be above the crew's heads, and not at the same height as the boom. The higher the radar, the further it can see due to the curvature of the Earth. So sometimes the dome is put on the spreaders halfway up the mast. So how is a radome constructed? A radome is typically constructed with a patch antenna and a horn flare. So the horn flare constrains the beam in the vertical plane to about 25 degrees, and the patches at X band which is 9.4 gigahertz. The patches are spaced roughly half wavelength apart. So this one has got you can see the patches here with a feed on each side, with a feed going in each direction. So the antenna length defines the beam width. So as I say, for an 18-inch antenna, it's about 4.5 to 5 degrees. And that antenna rotates inside the dome. A horn antenna is a long slotted waveguide, which is typically end-fed. So you can see the feed here, and you can see the slots, which are again typically around about half wavelength apart. So the feed comes down here and end feeds the array, and because it rotates, it has to have a rotary joint here, which in this case is done with effectively like a large coaxial connector. So there's a pin that goes into the waveguide to feed the microwaves into the antenna. So notice how the slots are across the waveguide, and that ensures that the antenna is vertically polarized, which gives a better result for avoiding reflections from the waves or sea clutter. There is also a polarizer that usually goes in front of this, but I've removed that in this picture for clarity. So that produces enhances the effect of the polarization that you get from the orientation of the slots. The slots are not all orientated at the same angle, so the ones in the middle have a greater slope than the ones at the end, and that tapering means that there's more power emitted from the center and less from the edge. So you get a kind of windowing effect, which tapers the beam shape. Otherwise, you just get a sine x over x function, which will give unacceptably large side lobes of about -13 dBs. So up until about 5 years ago, there was really the only type of transmitters used in leisure marine were magnetron transmitters and circulators. So here we see the magnetron, and that's actually an isolator, which and a filter, and then so the microwaves are emitted down through here, through the circulator, out through this port, up to the antenna, and then the reflections come back through the circulator and back through this port into the receiver. The circulator here is fascinating because it uses the spin of the electrons in a ferrite material, where the ferrite is surrounded by strong magnets, to actually cause the microwaves to go preferentially in clockwise direction. So the incoming signals come in from the middle port, and they're also fed, go around there in a clockwise direction. So solid state radars have been coming into the field as a result of the availability of gallium nitride amplifiers at X band, and the X band there's a band of 9.3 to 9.5 gigahertz, which is allocated to marine radar, and the gallium nitride amplifiers have significantly reduced the cost and increased the available power of solid state microwave solutions. What's interesting is looking at the actual energy per pulse. So a magnetron would typically have a pulse lasting 1 microsecond and 4 kilowatts, and so that would be about 4 millijoules per pulse. FMCW, which I'll talk about in a minute, is about 1.7 millijoules, and a pulse compression radar using a 50-watt power amplifier and a 100 microsecond pulse would have about 5 millijoules. So you can see that in ballpark terms, these are all quite similar in terms of their emitted power. So solid state radars also exist as FMCW. They have advantages of virtually zero minimum range, because because the transmitter and the receiver are designed to operate simultaneously. The receiver isn't blanked by the transmitter, but they also have the disadvantage that because the transmitter's on all the time, noise leaks into the receiver, so principally phase noise. So in my experience, the long-range performance beyond about 6 nautical miles is a bit of a limiting factor. That transmitter into receiver leakage can be solved by carefully cancelling the leakage in a vector canceller, but these are difficult to calibrate and tend to be used in military FMCW radars. But you can see that the way that the leakage has been helped with this radar is that there's a separate transmit and a separate receive antennas, and the horn flares here provide isolation between the two. So what does that minimum range actually mean in practice? This was taken in the Solent, and this was the Cardinal split buoy at the entrance to the Hamble River, and this was the pulse compression radar, and on the other side of the boat simultaneously we had an FMCW radar, and we were doing some measurements of the two, and this is the pulse compression and that's the FMCW, and in both, so that's where the radar itself was, and that's the buoy in both cases. And what you can see here is the actual reflection of the superstructure of the vessel, the bit where I'm standing, and that's also visible down here. And so the further improvements were made, and the minimum range is now down to about 7 meters, and typical magnetron's minimum range is 20 to 30 meters. So it's getting pretty good, but there is a difference between the two types of radar. So how does the FMCW radar work? It transmits, so this is the time axis and this is frequency. It transmits a continuous signal which ramps in frequency over time, and then it jumps back and then ramps in frequency and jumps back, and the target echo coming back is delayed, and so there will be a frequency difference between the transmitted signal and the received signal, and the frequency difference can be determined by doing an FFT on the received signal. And so this is the transmitted signal in the time domain, and that's the received signal is obviously also continuous. And then when you do an FFT on that, you get the target echo showing what the frequency difference is. So pulse compression radar, the minimum range, as I mentioned, about 7 meters, and we're typically talking about 40 microseconds, 170 watt pulses for a commercial ship radar, and leisure marine radars are kind of in that same kind of ballpark. And this was So how it works is a pulse is transmitted, which varies in frequency throughout the pulse, and then the received signal is correlated with that pulse, and the correlation that you get between the transmitted chirp and the received chirp gives you this shape, and is actually also a sync function. And so this is the auto correlation of a rectangular pulse, and this is the auto correlation of a chirp. And you can see that there are side lobes which last as long as the original. They last in time for the duration of the transmitted signal, the side lobes. So part of the secret of making a pulse compression radar is to suppress the side lobes. So here you can see what happens when you have multiple targets. That's the transmitted signal, and in time, or rather that's the received signal from a single target in time, and this is the received signal in time for multiple targets. And when you do the autocorrelation, this is what you get back, and you can see the correlation spikes here. And so this was actually a simulation that I took the results of from somebody else's presentation, and so we can see that the pulses, the targets are separated well. Well, you can't really see that in the time domain. So solid state radars can have a better resolution than a magnetron at short range, and so we can see here on the left is a magnetron radar, 4 kilowatt magnetron radar, and this is a pulse compression radar, and this is actually in the Hamble River, and these are pontoons with boats on, and the size of the blobs in the range extent indicates the range resolution. So we can see that we're actually separating these pilings here much more clearly in this radar than we are in this one. So it's a bit of engineering. This is the microwave board out of an FMCW radar, and it's separated into two sections. There's the transmit section at the bottom, and there's the feed pin there, which is kind of arranged to be like an SMA connector, and then there's a feed pin at the top for the receive signal, which is there. And so this is the receive pipeline, this is the transmit chain. So the transmitter starts over here with a local oscillator and a frequency multiplier, and there's a microwave filter there, and then it separates here into a Wilkinson divider, which allows multiple stages, two stages, to be paralleled up, and those two stages come all the way through here. I'll just zoom in a bit on that. So you can see these Wilkinson dividers here. So the signal coming in here separates into two, gets amplified and then recombined, and then it goes through a microwave filter before it goes to the transmit pin. So over here is the local oscillator, and the beating between the transmitted signal and the received signal is obtained by the receiver gets a sniff of the transmitted signal and heterodynes that to produce the received signal at 0 IF. So this is a Garmin pulse compression radar, and that's power amplifier underneath there. This is the transmitter. This is the receiver section, and the receiver IF and the transmit IF. And down here we have limiters, which prevent the receiver being damaged by another radar nearby, and then it gets fed round here. This is interesting in that it's actually a double heterodyne receiver, so it's actually got two IF frequencies, an IF frequency around about a gigahertz, and then a much lower IF. So all of these PCBs, etc., by carefully analysing with a magnifying glass, you can really see what's going on. Down here is the feed to this is the feed to the waveguide. So there's a feed pin feeding the waveguide here, and then there's the circulator for this radar. You can see that circulator is very much smaller than the circulator I showed you before for the Magnetron. And that's because of the lower peak power. So this is a Furuno pulse compression radar, power amplifier. This one has two microwave waveguides. There's a transmit waveguide on this side, and there's a receive waveguide on this side. And this is the receiver. This is the transmitter section up through here. And my guess is that they designed it with two separate waveguides, so it was compatible with the mechanics of a magnetron radar that it was slotted into, so they didn't have to change the mechanics at the same time as the electronics. So this is a Raymarine pulse compression radar, circulator, power amplifier, driver, transmit chain, circulator, receiver, and then here that's the receive mixer and that's the transmit mixer. And this is the processing chain and power supply and memory and flash memory here. So in the case of the Raymarine Quantum, the whole array rotates, and all of the electronics is fixed to the back of the antenna. And you can see the patch antenna, very much like a magnetron radar. So how are these radars used? Here we have a more traditional radar display, and the color of the radar denotes the intensity of the reflection, and this is the shoreline here. This is the Shell jetty, and this is the SO jetty on Southampton water. Over here we have the same information. The orientation is different. So unfortunately, when I took these pictures, this one was in head-up mode, so the boat is going that way, and this one it's north up, so north is there, and the boat is going that way. But you can see the Shell jetty here, and so it's easier for a lot of people to comprehend what it is they're looking at on a chart overlay version compared to the traditional. But there are details that you can pick up in this version that you can't pick up in the chart overlay version. For example, all the radar returns are shown in a single color, so you can't tell much about their intensity. So I'll touch briefly on AIS, or Automatic Identification System, although that's not really a radar. Why it's of interest is that often people ask, which would you rather have, an AIS system or a radar system? So AIS system has a transponder on the vessel and that's interrogated over a dedicated VHF channel and sends a response which contains the information about the speed and direction of the vessel. So this AIS display we can see here, so these are the actual vessels shown on the chart, and these areas here are the, if you like, the danger areas where those vessels are going to be shortly. What you can also see is that these vessels here are actually going off, appear to be going off in towards the shallows, and that's because they're down here, and in reality they're going to turn. So AIS is telling you what is happening at the moment and making a prediction where it's going to be in shortly, but it's always effectively behind real time, because it's the information when the transponder was last interrogated. So these show the predicted areas of danger. So this is AIS on top of a radar display, and you can see these are tankers moored against the Fawley refinery jetty. So there is an advantage in having both AIS and radar at the same time. The benefit of the radar is that most obstructions and small vessels don't have AIS responders. So here, for example, we can see these are posts marking the channel into the Hamble River, but they appear on the radar, but they are not AIS targets. And likewise, the Fawley jetty, which is a massive great structure, is not showing any AIS. So there is an advantage in the radar from that point of view, but the advantage in AIS is it also gives you an indication about where the vessel's going. So it will tell you, for example, that it's intended to go to Southampton. So if you're going along the Solent, you can tell whether the vessel is going to go into Portsmouth or whether it goes into Southampton. So I will talk about the more recent development, which is Doppler. And Doppler radar highlights in different colors targets that are approaching in red, because they could be dangerous, or receding in green. And the Doppler signal determines only the target's velocity away from or towards, in other words, only the radial velocity. And we use GNSS or GPS data to determine our own velocity over the ground, and if correct for that, so that you can tell the target's velocity over the ground. So we remove, in other words, we remove the Doppler shift due to our own vessel's motion, and the remaining Doppler shift due to the component of the target's speed over ground towards away is then applied to allow us to highlight targets which are in red or green accordingly. So coherent pulses are required to detect the Doppler shift. So Magnetron radar, every pulse that's transmitted has a different phase. A coherent radar, which is a requirement for solid state, each pulse is transmitted with the same phase, and the way that the Doppler works is that the change of phase from pulse to pulse is measured in order to detect the target's return Doppler frequency. So at X band, that's 32 hertz per knot. So X band, that's 0.603%, 32 hertz of the carrier, 9.4 gigahertz. So that's quite challenging. to get that to get everything to be stable enough. So this is what that looks like. Vessel, these vessels are approaching, and this is receding. This was actually the Isle of Wight ferry down here, and these vessels are approaching here. So Cowes, sorry, that's Yarmouth ferry. This is Cowes up here. This is Cowshot, and the vessel that our own vessel here was actually doing 62.4 knots. So this was a trial to ensure that the system worked with high-speed vessels. So we had two vessels in this trial. One which was doing 62.5 knots directly towards another vessel which was doing 30 knots in the other direction. So an approach speed of getting on for 90 knots. So this slide is from one of our trials where we were looking at rain clouds. So these are receding rain clouds, and these are approaching rain clouds seen in Doppler. This is what they would have looked like in a conventional non-Doppler. So we can tell that they're rain clouds because of the coloration, because they're less intense than the solid targets, and we can tell from the Doppler whether they're approaching or receding. So the benefit of that will be that in the Caribbean you get very intense squalls which can brew up very quickly, and the more warning that you get of those, the better. So I anticipate that future leisure marine radars will be better at detecting approaching weather conditions and be better able to display the weather and the Doppler data simultaneously. So this was that high-speed trial. So this was high-speed rib, and this was the one that was doing 62.5 knots along the western Solent, and the radar is mounted high on a radar arch above the helmsman. It was glorious weather that summer, and you do need to have some reasonable sea legs for some of these trials. As I say, the approach velocity was exceeding 80 knots, and radars are sampled systems, so they transmit a pulse and get a received signal, and so that happens multiple times. So radars are sampled systems, and the velocity will alias as with any sampled system, and positive velocities will become negative velocities and vice versa if the sample rate is not high enough. So this was aimed, that trial was aimed to prove that we'd actually got that right. And finally, thank you very much for your attention, and so some guidance here of things that I've found interesting in the work that I've done over the years. Is if you're interested in radar, then Skolnick is a really good book to get your teeth into, to get the principles, and that covers a lot of things in a great deal of detail, including things like sea clutter. And this radar tutorial was quite a good primer to get started. And then these are where I've taken some of the information for the slides from. So a special thank you for the knowledge and experience I gained whilst in the employment with Raymarine, but they bear no responsibility for any errors or omissions in this presentation. I'd like to thank my by friends and colleagues, past and present, at Raymarine and in the wider marine industry. They taught me a lot. And thank you for listening. And I'll hand you back to Nicholas for questions.
Thank you very much, Richard. As usual, I learned a bit from you there. So we have a few questions. The first one is from Phil. He asks, so is a radar effectively a short open array housed within a dome?
It is, yes. It's and in fact, some manufacturers a few years ago did exactly that. They took a slotted waveguide 18-inch open array and they put it inside a plastic dome. And it turns out not to be the cheapest way to do it, but effectively it's what it is. It's a short open array in a plastic enclosure.
From that question, what would you say would be the differences for you apart from that, the covering?
The main difference is that you, if you want to get good resolution, angular resolution, and you get more gain from a longer antenna. So the antenna gain is proportional to the length. So that a 6-foot antenna has much more gain than an 18-inch antenna. So if you want to have an antenna that will see a long way away, like 72 miles, for example, or 96 miles for a 6-foot open array, then you need an open array. But you can't make a 6-foot dome. So or it wouldn't be very pleasant to look at. So so each of the two types of radar have their uses. So a dome is really useful on a sailing vessel where you wouldn't want that rotating antenna to get tangled with things.
Thanks. The second question is from Robert Kitt. He's used RN, but I'm going to assume that means the Royal Navy. Here. The Royal Navy large vessels use nav radar at both 3 and 9 gigahertz. Do you see any use of 3 gigahertz in the leisure sector?
The part of the problem with the 3 gigahertz S-band radar is that to get the same performance out of an S-band antenna, the array needs to be 3 times as long. So a 6-foot, to get a performance of a 6-foot array out of an S-band antenna, you'd need to have an 18-foot long antenna, which would be a bit cumbersome. So the benefit really of S-band is it sees further, but the typical maximum range of an open array magnetron radar is 72 miles, which, because of the curvature of the Earth, is about is more than adequate. To get a range of 96 nautical miles, you'd have to have a radar on top of the Eiffel Tower, and the target would have to be the Empire State Building, to take into account for the Earth not to get in the way between the two. So when people talk about maximum ranges of 96 miles, you need to actually take that with a bit of a pinch of salt.
And thanks, Dan. So this is from Doug. How does radar distinguish between a signal from the host vessel, yet ignore other radar in the area?
How does a radar distinguish between its own transmissions and another radar, transmissions from another radar? Is that the question?
That's correct. It's a radar interference question.
Quite complicated.
Yes.
There is the time between each pulse is varied in a pseudo-random fashion, such that any pulse that is received from another radar will not appear to be at the same, have the same delay as the transmitted pulse from your own radar. So effectively, all of the radar blips from other radars get smeared across the entirety of the screen. They don't add up, unlike transmissions, the reception signals from your own radar. So typically you'll integrate 50 pulses, between 15 and 50 pulses to determine if something is actually a target. So the other radar the pulses from another radar will not integrate because of the pulse stagger, as it's called.
Can I add something there?
Certainly.
Isn't one of the other things that the other radar's transmission pulse is also very strong because it's not being reflected in many cases?
It is, yes. So there is a problem whereby there's another radar nearby. It can actually desensitize the receiver. So we have to put in limiters to make sure that the receiver isn't damaged by another radar. But the pulse from the other radar will not appear on the display by virtue of the pulse-to-pulse integration.
Doug has two other follow-up questions. How do Raycon and e-Raycon and SARTs manage to display? Are they transmitted at a reserved frequency?
No, if you take a SART just simply sweeps up and down the microwave, up and down the X band between 9.4, between 9.3 gigahertz and 9.5 gigahertz, and it effectively just makes a whole load of noise. And how it appears on the radar display is it appears like a Catherine wheel, because it's not. You know that those transmissions are coming from the same place, but they're not made to follow the transmitted radar signal. So a SART will get energized when it gets pinged by your transmission, and it will send a pulse out. But the pulse going out will typically be a sweep of frequency, so that to make sure that regardless of the transmitted frequency, the SART gets seen. But Raycons are more intelligent, and they will actually do things like time the pulses, the transmission between pulses, so that it knows it predicts when the next ping is going to be transmitted pulse is going to be sent by a radar, and sends a pulse back at the right moment. One of the key things with Raycons is trying to save battery power. So it tries to conserve battery power by techniques such as that. But in terms of frequency, no, they both transmit on nominally the same frequency as they receive, but they don't get that well. They don't aim to get that accurate, so they actually sweep over a frequency band.
The last one from Doug. Can we expect to see holographic radar in the future? Says that he understands it is good in the vicinity of ever-increasing wind farms.
I think that a lot of the issue with leisure marine radar is what customers are prepared to pay, and if the performance of what they've got now is good enough, then there's a limited scope for suppliers to actually make huge changes of increases in complexity. So I think probably the answer to that will be, if there's a demand, then products will get made to satisfy that demand, but the demand needs to be there.
Thanks, Richard. So the next question is from Steve Chill. What devices are typically used for signal processing?
So in the case of the solid state radar, the frequencies, the incoming received frequency comes in at a low IF frequency of the order of a few tens of megahertz, and that is directly sampled by a complex IQ channel ADC and fed into an FPGA, and then the FPGA then is used to down convert that to effectively 0 hertz, and then the radar processing takes place inside the FPGA. In the past, on Magnetron radars, the previous generation of Magnetron radars had DSPs and FPGAs, and the DSP did some of the signal processing, and the FPGA did a lot of the high-speed work associated with doing the down conversion. But we managed to get it such that we could get rid of the FPGA, get rid of the DSP and have only the FPGA to reduce cost.
And this one is from Paul Banjo. He asked, magnetron versus solid state, how do they compare temperature stability?
The answer to that is that they're both adequate. The temperature stability of magnetron radar is compensated, but as the magnetron warms up, the transmitted frequency decreases, but the receiver is always constantly tuning to pick up a portion of the main bang or the transmitted signal, and it always tunes to that. So as the transmitted magnetron frequency changes, so the receiver retunes automatically to that frequency. In the case of the solid state radars, that problem doesn't occur because they both have both the transmitter and the receiver are locked to a stable crystal reference, which has to be pretty stable, as we can see, in order to be able to do the Doppler processing. But the magnetron radars you can't do Doppler processing easily with a magnetron radar because the pulses have different phases on each transmitted pulse, and there were techniques in military radars that compensated for that, but there was never any leisure marine Doppler magnetron radar as far as I know.
So the next question is from Steve Cheel. Can low-flying aircraft, for example helicopters, ever be mistaken for vessels on the radar screen?
As you get more experienced in looking at the radar screen, you can tell what the shape of things are. So I could tell, for example, from that radar picture that we looked at earlier, that was actually one of the Isle of Wight ferries. And that's because I've seen those time and time again when doing radar trials in the solar. So as you get more used to what you see on the screen, you can see, for example, a line of buoys, and you know a line of targets, and you know that that's almost certainly a line of buoys. So aircraft will typically be moving faster than anything else on the screen, and so you'd be able to tell that whether something was an aircraft. If it was a hovering helicopter, for example, an air sea rescue helicopter doing a rescue, then yes, you would probably confuse it with a target. But in either case, you'd probably want to avoid it anyway.
The following question is from Paul Banjo. Radar versus sonar when it comes to detecting unidentified floating objects. I'm assuming he means on the surface. I don't know how that works with sonar though. Richard?
There is a significant problem with containers that have fallen off container ships, and several of the round the world race vessels have been damaged by hitting semi-submerged containers. The problem with them is that when they're in the sea, they're typically only an inch or two, possibly as much as 6 inches above the water. So the radar, they're quite difficult to spot for radar because they're typically buried in the sea clutter, and they're very difficult for sonars to spot because if you have a forward-looking sonar, then the problem is you also got waves. So it is a very difficult problem to spot semi-submerged containers, and at the moment there isn't a good solution out there in the marketplace that is good for that problem. And so yes, I would think that would be something that would be a great deal of interest if somebody could solve that problem.
New one from here. And so this is from Philip Benstein. I may have pronounced that incorrectly. An end-fed array has inherent squint. How is this catered for?
That's an interesting question. There's a bit of a cheat that goes on really, because the radar itself might not be mounted on the vessel aligned perfectly with the forward and aft direction of the vessel. So the customer or the installer has to calibrate the radar by looking at a target in the distance, by pointing the vessel at a target in the distance, like cowshot chimney, for example, and then they see the radar return and they line that up. And there's an offset control that you make to line the two things up so that your target of cowshot chimney and the marker which is showing you the direction of the vessel line up, and magically that takes care of the squint as well.
The next question is from Seamus Doyle. How do solid-state radars work with Raycons?
Generally, not well. The two technologies are really quite different from each other in terms of time. Raycons have been around for many, many years, and they are designed to particularly to pick up a high power pulse from a magnetron radar. So the receivers are not that sensitive, and they didn't need to be to pick up a 4 kilowatt pulse from a magnetron radar, for example. But when you have a much longer, lower power pulse, Raycons are simply just not currently, the ones that are deployed in the field are just currently not designed to detect a pulse that's of that shape. So the answer is that Raycon developers are actually changing the way that the Raycons are designed such that they will be compatible in the future with, or better compatible in the future. But unfortunately, it's just the laws of physics that mean that the radar, the Raycon's receiver sensitivity has to be much improved in order to actually detect the lower power pulse, regardless of its duration.
Thanks. The next question is from Steve Cheel. Okay. Are marine radar transmissions ever potentially hazardous to the crew?
I can say that for leisure marine radars, the answer is almost certainly not. It's something that has to get measured when the radar is first manufactured. In the case of solid state radars, the typical radar, the distance for which you have to be away from the antenna before it becomes hazardous is inside the dome. So you'd actually have to have your head inside the dome before you'd actually receive enough microwave power for it to become hazardous. There's actually a much bigger hazard of being hit on the head by an open array than there is from the microwave signal. And the reason is that the actual power is of the order of say 4 kilowatts, and how the radars have got the reputation of being a problem in this respect really comes from military radars, which are aimed to detect aircraft at hundreds of miles away and might have powers of the order of megawatts. So leisure marine radars are very safe.
Thanks. The next question is from Ian Cole. Are there any disadvantages to using Doppler radars?
Yes, there is the presentation of the Doppler radar picture, I think, is something that can be improved. The conventional picture shows you the intensity as a change in color, and that's good to allow you to see, for example, whether a signal is actually a wake off of a boat, or whether it's a rain cloud. And in the case of the ability to see targets in fog or heavy rain, that ability to differentiate between rain and targets is good. A Doppler radar, where it's showing the targets in red and green, is excellent for determining that whether those targets are going to become a problem, but you can't really so accurately tell what kind of targets there are. So the presentation, I think, is something that needs further work by the industry. And in terms of one thing that I think that the Doppler solid state radars are generally not as good at the weather, seeing storms a long way away, and I think that's something that can be improved, and that is again to do with the nature of the target reflectance, is what's actually going on in the rain cell, the actual storm cell, where you've actually got multiple reflectors which are moving quite quickly, and that becomes more difficult for a Doppler radar to see. But it also offers potential in the future to actually be able to do more to tell you about what sort of weather that is. So I think that's one thing that in the future the solid state radars will get better at, is their ability to tell you more about the approaching weather.
So we're at 8, so we're only going to take, let's say, 5 more questions. Sounds okay for you, Richard?
Certainly.
So we've got, next question is from Alex Wood. Given that solid state radar is continuously transmitting, what determines its minimum range?
FMCW is continuously transmitting, and the minimum range of an FMCW transmitter is effectively 0, because it's designed to receive and transmit simultaneously. The pulse compression radar, has a defined shortish pulse of say 20 microseconds, and so its minimum range is determined by the sensitivity of the receiver being degraded during the transmitted pulse, because the pulse is much stronger, of the order of tens of watts instead of tens of milliwatts. So it's the minimum range of a pulse compression radar is not zero, but it's getting pretty good, down to about 5 meters.
So, the next question is from Phil. How do you see radar developing next? We've had Magnetron since the 1940s, and we're only now seeing some solid-state units. What's next?
I think that there's work to be done on presentation. The Doppler radars are relatively recent in the field and new in the field, and presenting the information, all of that information that you can see, the chart information, the Doppler velocity of the target, the AIS information, and presenting all of that simultaneously on the screen, I think is going to be open to further developments and improvements. And I think in terms of solid state radar, probably the developments we'll see is them getting better, longer, more powerful, and as the cost of the transmitters decreases, so they will use more power, which will increase the maximum range. And I think they will get better at detecting weather, and I see the development there as the ability to differentiate between different types of weather.
So, and next question is by Ian Doyle. He asks, do you see any developments that will make solid-state radars like sharp-eye cheaper and therefore adopted more widely by the leisure sector?
Yes, the principal cost of a leisure marine solid-state radar is associated with the cost of the gallium nitride power amplifier, and the costs of those are following a kind of Moore's law, where they're halving every 2 years probably. So that will reduce the cost. Probably you won't see that as a reduction in cost to the user, because what will happen is that the radars will get better at the same price. That's just the law of marketing.
The next question, penultimate, will be, how would you compare the relative spectrum efficiency and any problems of mutual interference between magnetron and or solid state radars also?
Yes, that's a good question. A lot of work has occurred over the years to actually make magnetron radars not interfere with each other, and solid state radars are relative newcomers. So the problems between mutual interference, well, Nicholas and I both actually studied, and we did some simulations, and we did quite a lot of work to actually get that pretty good. The problem that you have, I think, in the field is where you have a very old magnetron radar that might be 20 or 30 years old on a vessel, probably doesn't have the level of sophistication in terms of signal processing that a newer one would have. So probably a 20-year-old magnetron radar will show up more interference from a solid state radar than you would get for newer products.
And to close, I mean, I know we have a few more questions here. We'll maybe try to see a bit about them via, I don't know, EIT. The last question is by Patrick Higham. How big does the power supply have to be?
For a magnetron radar, the typical power consumption while it's actually operating is, well, for a 4 kilowatt dome, it's of the order of 30 to 40 watts. For a solid state radar, it takes about, well, 15 watts roughly. So a solid state radar for the same performance takes a third of the power